at the last minute to join us on the panel. Aram, of course, was the inaugural speaker in this series, and he's worked extensively on algorithms, including, of course, the Hill algorithm for linear algebra. And then finally, Matthias Treuer is joining us from his yacht, and I don't know, where are you, Matthias? I'm
close to the Canadian border, to Stewart Island.
Great. So
we sailed here this morning, anchored here, and I have reception because the antenna is way up on the mast, and that way I cannot escape Umesh. Wide range. Without that antenna, I could not have called in, I could have relaxed and have lunch. But now I'm here with you, and that's great.
Great to have you back, Matthias. As you remember, Matthias gave the colloquium 2-3 weeks ago, and he's of course thought long and hard about what you can and can't do in near-term quantum computers, or even longer-term ones. So just starting off this panel, I'd like to invite the panelists to give short 2 to 3 minute reactions to Ignacio's talk, as well as to discuss some of the main themes, which were, first, the theme that he ended on, which was digital versus analog simulation. Is there a way that we can meaningfully talk about what happens? Is there a way to talk about asymptotically what would happen with analog simulation, and whether one can get advantage with analog simulations, and also how these would scale with as the system size goes up, and of course then there are questions about analog simulations, in terms of well, since we have great experimentalists on the panel, what are the challenges and possibilities with experiments in quantum simulation, as well as eventually where can we go with them, beyond applications in science, which are obviously quite important. So possibly can we, Immanuel, would you like to kick this off?
Sure, I can start. Well, thanks for having me on the panel. And yeah, so maybe I touch on this digital versus analog side first. And so my feeling is, and this was maybe substantiated also with work that was done actually with Matthias and Andrew Daly, and Matthias can comment on that work later on, is that if you can implement a certain problem right now on these noisy intermediate scale quantum devices in an analog way, then probably for sure you have an advantage in doing it that way in terms of how long you can simulate, for example, the dynamics of the quantum system, how good you can simulate the dynamics of the quantum system. So from this comparison with Matthias, what we found was that, the amount of gates and qubits you need to do it in a digital fashion quite far surpasses anything that's possible right now. So the problem is, of course, the caveat is the if you can implement the problem. Of course, the nice thing with the digital approach is, in principle, it can be universal. But of course, well, we know in practice that means you need full error correction, but so that also has an if attached to it. But it is more flexible. It can do more things that you might not be able to implement directly. So I think that puts, places for me the point, if you can realize your problem in an analog way right now on the devices we have, and probably for the next few years also, if we have this step to go towards fault-tolerant quantum computers, this will be a main area of application for these devices and making scientific discoveries beyond solving trivial problems. I mean, where we really will have see new things coming out, learn new things, push theory. I think this is really going to push the frontier in this field.
Great, thanks, Immanuel. Actually, I think it might be nice to alternate experimentalists and theorists, but I just wanted to pick up on something you said about, well, digital simulation, of course, would be universal, So I just wanted to throw out one could think about analog simulation also being programmable to some extent, and so could there be a notion of actual, some sort of universality, even in the absence of error correction? Could it be programmable enough to be, well, maybe either universal or at least a very flexible kind of quantum computer that was analog, even though it was not, there was not error correction. Okay, possibly. Shall we move on to Aram? Would you like to?
Hi, thanks, Umesh, for having me on the panel, and Matthias, it was a very nice talk. Thanks for that. Yeah, so I have a few thoughts about simulation, which I don't know how actionable any of them are, but one thing that occurs to me is that, as computer scientists, we're used to scaling with problem size, but maybe for physical simulation, the precision scaling is more important. I have colleagues who do lattice QCD who are trying to simulate nuclei, and they only have to get through the periodic table and then they're done. But the precision scale in some ways is more daunting than the size scaling. And also, as the physical system gets larger, it doesn't, unlike most things are not like quantum computers, they don't remain coherent on very large length scales. So that seems, I don't know fully how to grapple with that challenge. And there's some relation between precision and dimensionality. Like if you talk about increasing the number of orbitals, right, then that's a way of getting at precision. But that seems like one thing to be thinking about. Another thing I was thinking related to the digital versus analog question, one way to think about an analog simulator is that it's imperfectly programmable, of course, which means that you can access some range of Hamiltonians, but one thing that comes up in quantum simulations is we have a target evolution, and maybe it's within the range of what could be achieved, but we don't know how to program it. So, for example, we do a Trotter evolution, even though maybe there exists a better way to get there, because we don't know how to get, we don't know how else to come up with a gate sequence. And so you could imagine that you have, let's say, an analog quantum computer where there's some always-on interaction, and then there's some other term that you can turn with a dial, and you're trying to drive to a particular point, and there are Trotter errors that are high-order terms, and you could get rid of them if you took exponential time to do a full classical simulation and figure out the optimal path. But of course, that would defeat the whole purpose of the simulation. And so we may get into situations where there's sort of some kind of triple trade-off between, how much compilation time you want to take, what kind of error you end up with, and how many quantum resources you want to devote to the problem. And that's another thing which I feel I'm bringing up these points because they're interesting, but they may be hard to study, maybe hard to make any progress on them. And the final thing I think would be interesting to study is combining these things with classical simulators, which some people have done, combining classical and quantum tensor network contractions. But there seems like a lot of room there still.
Thanks, Aram. Turn to Misha.
So yeah, thank you, Umesh, for invitation again, and actually thanks for running this great seminar series, and also to Ignacio for inspiring talk. So maybe I will try to kind of pick up a little bit on your last question about kind of programmability aspect. So indeed, you could kind of quantify, almost all quantum machines in terms of like several axes. So one of them, could be number of qubits, another one is, coherence, and the first axis is, programmability. And so in principle, if you have analog quantum simulators, which are fully programmable, they are, by definition, universal. In fact, you can run, at that point, the difference between digital and analog basically disappears. You can always run analog device as a sequence of the gates. And what I would say for that is that perhaps an interesting challenge, and it's also related to maybe some of the other things you mentioned, kind of applications beyond, quantum physics. I think it's an interesting challenge for maybe computer science to try to really start, thinking. I mean, it's in a way, this kind of digital quantum computers, it's relatively easy to map onto conventional kind of gates and sequences. I think analog devices are kind of a different, beast a little bit in the town, right? And I actually think that this is a very special opportunity because, as Immanuel said, that in terms of, let's say, pick some, interesting parameter, I don't know, degree of entanglement, system size, like the duration of the kind of evolution. I would say, in particular, programmable analog devices, programmable quantum simulators in general, are capable of kind of solving, scientific, problems and the problems in quantum physics at a level where I think, kind of conventional quantum computers have really hard time to compete right now. So, and I think that is really, I think that's a very, very special opportunity, in our field, and I think this kind of opportunity is maybe kind of twofold. On one hand, this is, something we talked about a couple of weeks ago about this kind of age of quantum discovery, where I think, basically we can, push the systems to corners of Hilbert space where no one has been. And, frankly, at this point, whenever you go to this new corner, you always discover something. You could then go back and ask, okay, can you somehow devise some, tensor network to simulate it? And sometimes you can, but nevertheless, to a priori, you wouldn't know that you could even find something there, right? But on the other hand, if we start building this bridge to CS and kind of, more in a more substantial way, perhaps we could also start asking, and answering the questions, can the systems be used beyond just the domain of quantum physics, where they are very, very natural?
Great, thanks, Misha. That's really interesting. Matthias, would love to hear what you have to say.
So, listening to the great talk, but by Ignacio, I had two comments. One was about the question about ground states versus dynamics. My view there is that ground states are classically easier. Ground states is what if you looked at for decades and centuries, but it's not because we don't want to study dynamics, but that dynamics is typically hard, too hard. We don't have yet the theories to predict dynamics always. And one reason for that may be that we don't yet have, or that we didn't have ways to actually get controlled data. And so with the simulators we have now, there is a big chance to use them to actually simulate simple systems that will then allow us to discover new theories for dynamics. And since that's the hard thing classically and easy quantumly, I think that could be a great way of starting there. And generally, while we would love to have a digital machine that can do any model, it should be sufficient to have some analog for now to study many models, and like for the dynamics case, use the results of of the machines we have now to give us your data that can be used to validate or calibrate or to invent the new classical methods. So I think there's lots we can do. Because what would I do if I had a gate model machine with a few 100-year qubits? I would use it to study dynamics. I would use it to study spin models, to see Hubbard models. But those we can do now. To do chemistry will take something much bigger. So it starts with the same models, and that's what we can do to now already. So I think we should use the machines where they are good, namely for the dynamics. Use them as something analog, and use it as Misha said, to find new physics.
Great, thanks a lot, Matthias. So I want to turn to Ignacio now for his reactions, but before that, let me just say once again, something about dynamics that maybe I'm just not seeing it clearly as a computer scientist, but my naive view is that ground states hold still long enough that we can look at them and look at them repeatably. But dynamics in quantum systems, it seems, well, you have this trajectory you cannot even see. All you can do is sample from the final distribution. So it would really help me to understand, scenarios. In what way is dynamics going to be useful? How would you profitably use it, once we are able to do those simulations? So, at some point, it would be interesting to hear.
So I'd say what you say is just why it is so super hard to actually have data for that. Why we can't really model it, but we would need it for transport simulation, for magnetization changes, nucleation, phases. How hard drives here switch bits, for example. So there's lots of things that we can't really measure because it's so fast.
Mm-hmm.
And that's why we don't have the theory yet, because we can't check it and test it.
Mm-hmm.
But since we can now on the machines here that Misha builds and others build, and you have the Immanuel and so on, then that's where we can learn about dynamics, phase nucleation, transport, transient effects in transport. There are many open questions there.
Great. Thanks, Matthias. Ignacio, I'd love to hear what.
Okay, so I think that I could not agree more with what has been said. And actually, I skipped one of the transparencies, and I'm going to go through that a little bit to show my agreement. So at the end, I wanted to say, so why do we want quantum simulation? So this was my last transparency. So what if we have now a quantum simulator that has 100 to 200 qubits? What can we do with it? And so I think that I would say 4 things at least. So one of them is to solve specific problems. Okay, so maybe somebody has a Hubbard model, and with a classical computer with exact calculation, we can only go to 40 qubits. And so with 100 qubits, we may learn a little bit more and then go a little bit in the direction of, getting more information, improving a little bit the classical computers. Another one is provide understanding. So sometimes in many body systems, when you have a physical phenomenon that you observe, you measure, you would like to get around it and to try it. And what happens if you change something, and to have a mechanistic model of understanding it. And I think that these quantum simulators, it's really like that. You just see it. And one example is what happened, like in high energy physics. If you start talking to people in high energy physics, it's very abstract. But whenever you start talking about tensor networks or quantum computers, then you see it in a completely different way. That's a different perspective, which I think that from the scientific point of view can open some doors. Another one is what Immanuel says: curiosity-driven research. Okay, so you can start just checking, looking for new phenomena that you could not even imagine that they would exist. I mean, Mikhail has an example of that with his scars, and so you can just try something and they pop up many things that come out. But the most important part, and I insist that in many talks for me, is benchmarking theories. I mean, Matthias was talking about time-dependent theories, but also time-independent theories. I mean, we, as you know, we are working also on tensor networks, on the developing of algorithms of tensor networks. And one of the problems that we are facing is that there is no way of benchmarking in many cases. So you have some tensor networks and you think that it will work. And then you have some arguments why it will work. But if there was an experiment with 100 qubits or 200 qubits, that you know that it works or it may not work or whatever, you could change, check with that. I think that this would allow us to develop many, many methods, numerical methods or computational theoretical methods that at the moment we don't have. So working theories with experimentalists, in that sense of experimentalism, I mean, providing this wonderful tool, new ideas, new discoveries, and with theories, I mean, bouncing back these ideas and with new algorithms and methods, I think that it could give a huge advance to the development of many-body theory in general. And I think that this is the most important one, rather than some specific examples. I think that this development that they can allow us, that has been missing so far.
Mm-hmm. Oh, that's great. Yeah, thank you. Maybe I should see if anybody in the audience has a question.
So I don't see many questions here. There is a question from Rob Cook. So it says that our speaker made connections between extensive and intensive quantities and robustness to errors in quantum simulation. I believe there is a conjecture that asserts roughly that anything you can compute on a quantum computer without error correction can be computable on a classical computer. But I'm wondering if panelists have any comment on that.
I don't know the conjecture, but I think one challenge with formulating something like this is that error correction does not have a precise definition. Error correction is just a kind of software technique we use. And so there's no real bright line between quantum computers with and without it. There are some heuristic algorithms like Isaac Kim and also Kim and Swingle have some algorithms for doing certain kinds of quantum simulations of systems that have bounded correlation length. And so you might say that if those, it's possible that the arguments that lead those to work quantumly would also lead a classical simulator to work as well. But I think if this were true, it probably would be in some special cases. So I think, and I guess one more thing I'll say is this kind of gets back to some of the precision questions. So this is one thing that we know for random circuits. I'm just going to say this because we know it rigorously, is that if you have random circuits, like the kind that Google did for the quantum supremacy experiment, and each gate has an error rate epsilon, then there's a classical simulation, and the runtime is like exponential in 1 over epsilon, or exponential in 1 over epsilon squared. I think exponential in 1 over epsilon. And so that is, polynomial time if epsilon is constant. But if epsilon is 1 over 100, then that's still going to be out of the range of any classical computer. So it may well be that if we don't do error correction and we just let the errors accumulate, then there is some, formally speaking, there's some polytime classical algorithm, and still that could lead an enormous amount of room for big quantum advantage.
Yeah, thanks. There's a question in the chat. Yuan Liu asks, about this question about fermionic type simulations like electronic structure problems. So wouldn't there be an advantage to using a fermionic quantum simulator? Or what would the, I guess, just translating it, what are the prospects of actually implementing that efficiently in the lab?
Well, that's what we're doing. I mean, that's exactly what we're doing. And Markus Greiner, our team in Munich, others are working on this by directly using fermionic particles that simulate electrons. So you don't have to map this problem onto, in a standard qubit-based quantum computer, you would have to map the electronic problem onto the qubit system, and that already carries an overhead with it in the number of qubits and the number of gate operations. But for us, we can do it directly. So we just have the fermionic problem directly. So that's, of course, a huge advantage in terms of how far we can then push this. So for this specific problem, I think it's a very good example. If you can implement more complex terms there, you really are pushing this in a very, very interesting direction. And right now, I think the simulators are at the point where they're just about, I think, on the same level with the most advanced simulations. So I think getting a little bit colder, for example, in temperatures already, I think, would bring the simulators into a regime where, again, it would push theory. I think this is always back and forth, as Matthias has explained, very interesting back and forth between theory and experiment. And but now we're really already at this very interesting point where we're challenging theory already to come up with the results. I want to just add also one thing I think is very important for me, was very important to learn that, we have, through these quantum simulations, we have learned how to use new observables to characterize quantum many-body states, especially like non-standard, non-local observables. I mean, Misha had very nice recent results on this. We have been studying this also for a long time now. And really this, I think, broadened the mindset of the whole theory community, because the people were not thinking of this. The condensed matter physicists, they were thinking in the standard 2-point correlation functions, what you can measure in a neutron scattering experiment maybe. And really, I think this brings a whole new set of discussion to the table of what we can measure and how we can understand those phases of matter. Also dynamics, of course. I think this is very exciting. And finally, one final point, Umesh, if you allow me, where you asked, why is it interesting, dynamics? I think we should also mention that dynamics is very interesting for creating interesting resource states, for example, for metrology. This is something that can be super useful application, maybe as an outcome. If we can create metrologically interesting resource states for clocks, for measurements, and that's happening. I mean, Adam Kaufman, Manuel Endres are working on these things, so for example, and this is a very exciting direction for me as well.
I see. So, and just to go back to the point you started with about the fermionic simulators. So could you quantify that a little bit? So, if you were to take a suitable problem of your choice, what are the kinds of resources you would need to actually solve that, and how close are things now in terms of what resources you can bring to bear in the lab?
Well, so typically the system sizes are a few hundred particles right now. I think we'll see few thousand. And for bosons, we've already moved to a few thousands, and I think this will happen for fermions as well soon. So a few hundred. We can detect spin up, spin down, holes, doubly occupied sites, so we can make a full measurement in that occupation basis, spin resolved on every lattice site. So it's like getting a snapshot from a quantum Monte Carlo simulation, basically. And from that, you try to construct interesting correlation functions. So that's what we're doing in the lab. And yeah, that's basically where the systems stand right now.
Mm-hmm. Very interesting. Are there any other?
There's a question by Frank Vastrate on Q&A. So it says, Metropolis type algorithms have acquired a quasi-monopoly for simulating thermal states of classical interacting systems, mainly because of existence of smart update schemes. What is the prospect of quantum Monte Carlo methods that Ignacio talked about in that respect? Like, how do you design interesting updates.
So I don't know who should answer that. Matthias is the expert here on quantum Monte Carlo.
Okay, so I can mention here something there, namely, it will be important to always have the Markov chain to mix rapidly. And when we looked at the quantum metropolis algorithm first, we were worried that might mix very slowly. And then when we looked at it, we found out that that's not the case, that it's extremely fast in mixing. And down. But when you do quantum metropolis, then you're in an energy eigenstate, and that will be all up plus all down, or all up minus all down. And mixing between those two can be done very easily by a local clear sigma C operator. So it's extremely easy to mix those states quantumly. So the answer is yes, we have to look at the algorithms that mix fast, but the classical intuition might be misleading, because what we do is we take an eigenstate, we apply a local update, but then again we project on to an eigenstate, and that projection is totally non-local. And because of that, I think it will mix much better than classical algorithms, but that's something we need to look into much more.
Thanks, Matthias. Sorry, I think we should, this is pretty close to, we should bring this to an end, but I just wanted to very quickly ask one more question for the experimentalists, Immanuel and Misha. So in terms of doing interesting simulations, what do you think is holding, what's the bigger obstacle? Is it number of qubits, or is it somehow the fidelity of the operations? Where do you see things going? How do you see things progressing from here?
So I already mentioned, I guess in my mind, there are kind of three axes, in which you basically have to push the system simultaneously. Okay, number of qubits, it's a simple one to understand, but if you have a lot of qubits, but their coherence is very bad, there is nothing, you don't gain anything, right? But the third axis, as I already indicated, this is a programmability axis, right? So basically, regardless of what you want to do, if you want to do quantum computing, of course, you want to have it more and more universal. If you want to have, do quantum simulations, you would like to basically implement more and more complex models. Basically, these are the three, I think, kind of very important, directions which have to really be, kind of advanced. And, maybe also connected to one of the earlier questions, Umesh, about quantum dynamics, I would say that, quantum dynamics, especially non-equilibrium dynamics, is, I would say, really the central issue in the entire field of quantum information. And it's, this was already, I'm kind of repeating what others have said, basically, creating entangled states, which are somehow, like, robust, resilient, right? I mean, entanglement is clearly a resource, but if you have your system entirely formalized, I mean, this is not a useful entanglement, right? I mean, what other states which are, have interesting entanglement properties and useful, but, they are still kind of in some way controllable, right? So, I mean, what about metastable states? A lot of phenomena in nature, look, I mean, the entire, Bose-Einstein condensation is not a ground state. The starting point of all experiments by Immanuel and others is not a ground state of the system, but nevertheless, it's a super useful kind of, very relevant kind of state. And, of course, I mean, that also connects to what both Matthias and Ignacio mentioned, is that, right now, our understanding of this non-equilibrium phenomena, our theoretical understanding is really, really limited, And, the hope is really that through improving this coherence, number of qubits, programmability, also improving measurement schemes, looking at, ways to quantify entangled quantum matter, which is extremely non-trivial, right? That's a hope we can really, push, also both theories, physics theories, but maybe also, computer science theories,
Yeah, great. Thanks. That was very helpful. Yeah. Well, thank you. Thanks. All the panelists and to Ignacio for wonderful discussion. I've posted a GatherTown link for anybody who'd like to, join for an extended discussion. Yeah, I just want to, thank you all and see you next week.
Thank you.
Thank you. Great to see you all.
Hi, everyone.
Bye.